Hello, I'm Vasilopoulos and I'm going to present you the work Reactive Planning for Mobile Manipulation Tasks in Unexplored Semantic Environments, done with my colleagues Yiannis Kantaros, George Pappas, and Dan Koditschek at the GRASP Lab of the University of Pennsylvania. When we look at the problem of mobile manipulation of movable pieces in the robot's environment, which is known to be P-space hard since 1984, we can see that there exist reactive vector field-based approaches in the literature that either assume that each object in the workspace is actuated, or that there is only one actuated robot that has to pick and manipulate other passive objects, but there are no obstacles in the environment. Other researchers have also focused on the problem of navigation among movable obstacles, using heuristic approaches that assume a discrete environment on which sampling-based methods are applied, and they let the robot interact and push static or movable objects when a solution cannot be found. More recent approaches have also examined the problem of recognizing whether a particular obstacle is movable or not, and identify the dynamical properties, and replan online when an object, like the table shown here, does not move as expected. What was more interesting to us was that this problem of mobile manipulation and object rearrangement is intrinsically a task planning problem, and linear temporal logic has been employed for many years to encode tasks that involve navigation. Of course, past work has used just discrete abstractions of continuous dynamical systems to capture robot states, and replanning is again needed when something unexpected happens. But recent extensions showed how to eliminate this requirement and employ linear temporal logic in unexplored environments for a single or multiple robots. So in this work, we wanted to see whether we can transfer these results and use logic planning to solve mobile manipulation tasks in unknown environments, whether we can eliminate the need for constant replanning and also scale with many objects, and finally whether we can give any formal guarantees. For our problem formulation, we assume that we have a robot equipped with a gripper and a local sensor field of view. The environment consists of familiar but unanticipated obstacles that the robot can recognize and localize with its sensors, convex obstacles of completely unknown shape and placement, and also movable objects whose positions are known to the robot. The robot's task is to visit some known regions of interest and apply one of the following three actions: move, grasp object, or release object. To specify the overall task as an LTL formula, we define atomic predicates that are true when the robot takes an action at a particular place and false otherwise, and we combine our predicates with either Boolean or temporal operators to form an LTL task specification. For example, if the robot's goal is to rearrange the three objects counterclockwise, the LTL formula simply asks the robot to eventually grasp object 1 and release it to the location of object 2, then grasp object 2 and release it to the location of object 3, and finally grasp object 3 and release it to the location of object 1. The goal of the robot is then to generate the actions to execute online, translate these actions to point navigation tasks, and finally execute those tasks while avoiding obstacles. To make the problem more realistic, since we work in unexplored environments, we also ask the robot to detect online if a task is not feasible because an unexpected object or obstacle disconnects the robot's free space, and either locally amend the provided plan by disassembling blocking objects, or report failure and request a new action. The architecture that solves this problem looks as follows. Given an LTL formula, which in this example asks the robot to eventually navigate either to region 1 or region 2, we translate the LTL formula into a non-deterministic Buki automaton that acts as our symbolic controller. The symbolic controller is responsible for providing the robot with one of the three actions by performing a search on the states of the automaton based on some distance metric from the current state to the desired state, and provides completeness guarantees assuming that each provided action is actually feasible by a lower level controller. An interface layer translates this action into a point navigation task and a gripper command, realized by a reactive vector field controller with provable guarantees of target convergence and collision avoidance using sensor feedback. To account for blocking conditions, the detected objects and obstacles are fed into a topology checking module that checks whether the robot's free space has changed, whether the task is feasible, and also outputs the list of blocking movable objects if the task is not feasible. The interface layer uses this information to decide whether blocking movable objects need to be removed, and also update the needed parameters for the symbolic action implementation with the reactive planner. Once a particular action is finished or the robot reports failure, the interface layer asks for the next command from the symbolic controller. This whole process is run online. Focusing on the reactive vector field controller from prior work, its fundamental idea is to construct increasingly simpler but topologically equivalent environments, find a smooth map that is a diffeomorphism from the original environment to a model environment where all obstacles are convex, apply a doubly reactive navigation strategy in the model environment so that both the trajectory and the associated vector field are generated online as the robot explores the workspace, and finally pull back the resulting vector field to the original environment using the Jacobian of the constructed map. To do this, except for the physical space that the robot discovers as it navigates to its goal, we also define the semantic space that includes all recognized familiar obstacles and the observable portions of unknown obstacles, the mapped space where all overlapping obstacles in the semantic space are consolidated in real time, and finally, through a series of intermediate spaces, the model space, where all mapped space obstacles are either transformed to disks or merge to the workspace boundary to form a convex environment. In that convex environment, the robot is commanded to just follow the projection of the global goal onto a local free space around the robot placement. It can be shown that this strategy guarantees both collision avoidance and convergence to the global goal. With these capabilities in mind, if we have a workspace and a robot at X that needs to go to X star, but whose free space is blocked by a bunch of movable objects, the topology checking algorithm is a low-frequency loop that does the following. First, it finds all the connected components of the robot's free space and picks the component that includes the robot location. It then forms the enclosing free space necessary for our diffeomorphism construction as the convex hull of that component. If the goal also belongs in that component, then our reactive planner guarantees convergence. In a different case, the goal is blocked and we have to identify if that happens due to movable obstacles or static obstacles. So what the robot needs to do in that case is to identify all movable object clusters and check if the union of the free space components with these clusters includes both the robot location and the goal location in the same component. If that's not the case, then the goal is blocked by fixed obstacles and the task is infeasible. Otherwise, the goal is blocked by movable objects. So, in that case, the LTL execution is interrupted, the robot switches to a fixed mode, and first constructs a connectivity graph that connects free space components to movable object clusters. We can then simply backtrack from the free space component that contains the goal location to find all the blocking regions that need to be disassembled. So then the interface layer takes over and greedily removes all objects in those blocking regions by using the vector field controller and the new action, which we call disassemble object, that simply pushes an object over the boundary of the free space until specific separation assumptions are satisfied. Once this is completed, the robot returns to LTL mode and finishes the interrupted subtask. We include a set of simulation examples to demonstrate how the proposed architecture works. In the first example, the task is to navigate first to either region 1 or 2, then take object 1 to region 3, and finally object 4 to region 4. The robot starts navigating to region 1, detects that it is blocked by a fixed obstacle, so it switches to region 2, detects that this region is blocked by a movable object, and disassembles that object to complete the subtask. Then it proceeds to move the rest of the objects as necessary by first disassembling any movable objects such as object 2 or object 3 that block the desired configurations of objects 1 and 4. This example shows how this algorithm can easily scale to multiple objects for rearrangement tasks even though the generated trajectories by the vector field controller are greedy and not optimal. Here, the task is to rearrange the 4 objects counterclockwise, easily captured by a sequence of grasp and release actions. The robot starts moving to the first object, grasps it, but then realizes that the destination position is blocked by the second object. So it first moves the second object out of the way in order to move the first object in place. It keeps locally fixing such actions until eventually all 4 objects are placed to the desired locations. Even though the generated task sequence is not optimal, the robot eventually completes the task without the need of an external deliberative planner and with a very simple temporal logic specification that asks to grasp and release the objects in a specified sequence. Finally, we can perform more interesting temporal tasks, such as visiting 3 regions infinitely often, similarly to a patrolling scenario. In the first run, the robot removes the blocking objects out of the way and then keeps visiting each of these regions in sequence. At the same time, it avoids all unexpected obstacles in the environment to complete each assigned subtask. Future work will focus on providing end-to-end instead of component-wise formal guarantees, extensions to multiple robots for collaborative manipulation tasks, as well as physical experimental validation with different mobile manipulators. Thank you for your attention. We look forward to addressing any questions you might have during the allotted virtual slot at the conference.